Hey, welcome back. In this video, we're going to continue discussing the Turan numbers of cycles. In the last video, we went over the Turan numbers of odd cycles. So we found sharp bounds on the Turan numbers of odd cycles. We found that all of them are approximately n squared over 4. So more precisely, we saw how to show that exn c2k plus 1 is approximately n squared over 4. And this is for each k greater than or equal to 1. So we already knew this a while ago for k equals 1. So when k equals 1, we get C3, which is the same as K3. So that's the triangle. And we knew that the Turan number of the triangle is the floor function of n squared over 4. And we see that any other odd cycles, their Turan numbers are around the Turan number of the triangle. We also talked a little bit about even cycles in the last video. So we discussed the Kováry-Soh's-Turan theorem again. So that says that the Turan extremal function of the complete graph with parts of size r and s. So we can draw it like this. We have r size, s size over here, and all possible edges between the parts. And it's bipartite, so no edges within the same part. This has an upper bound of n to the 2 minus 1 over r. And by symmetry, we also have an upper bound of big O of n to the 2 minus 1 over s. And when r equals s equals 2, we can say ex of nk22 equals big O of n to the 1.5. So the Kováry-Soh's-Turan theorem implies that. We proved in the last video, we provided a construction using some facts from number theory that exn of k22 equals omega of n to the 1.5. And the reason why I'm talking about k22 is because k22 we saw in the last video, and we've seen this before, it's the same as the cycle C4. So k22, this complete bipartite graph with parts of size 2, we can also draw it like this. So if this is our left side, this is our right side, we can draw it where here's our lefts and here's our rights. And so these bounds that we got for the Turan number of k22, they also give us sharp bounds for the Turan number of C4. So we can see that exn of C4 equals theta of n to the 1.5. So we proved this in the last video. And so that's exn c of 2k for k equals 2. So that's the first non-degenerate even cycle, because C2, that's not really a cycle. C2, that only has a single edge. You can't have double edges, so it doesn't make sense. But the first actual even cycle, C4, we know its Turan number, and we proved it up to a constant factor. We proved that it's theta of n to the 1.5. There's also some other even cycles for which the Turan number is known up to a constant factor. So there's this general theorem that was proved, the Bondi Seminovic theorem. And what does this theorem say? Well, under that text, it says that the Turan number of the cycle C of 2k is equal to big O of n to the 1 plus 1 over k. So in the case k equals 2, this is just saying big O of n to the 1 plus 1 over 2. So we know that's big O of n to the 1.5. So we've already seen that the Bondi-Seminovic theorem is sharp when k equals 2. So the last video, the construction we did, this lower bound, that proves that the Bondi-Seminovic theorem is sharp for k equals 2, up to a constant factor. It's also sharp for some other values of k. We're not going to go through the proofs for those, but I'm just going to mention when it's known to be sharp. It's known for k equals 3 and k equals 5 that the Bondi-Seminovic theorem is sharp. So it's already been proved for those cases. For all other k, it's an open problem. So there's a conjecture for the other k. The conjecture is that the Bondi-Seminovic bound is sharp up to a constant factor. So this is the conjecture. And only the upper bound is known. And the lower bounds, besides k equals 2, 3, and 5, are not even within a constant factor of the upper bound. So these are all open, even to get it up to a constant factor. Now we're not going to discuss the full proofs of the best known bounds in this video. We're just going to discuss a general lower bound that's known for the even cycles. So we have this general upper bound for even cycles. We're not proving this one, the Bondi-Seminovic theorem. I'm just stating it without proof. But the lower bound, the general lower bound for even cycles, which doesn't match this, and it's not even close to conjecture, but it has some dependence on k at least, and it's in this last bullet. So we're going to prove this general lower bound. So you can see n to the 1 plus 1 over 2k minus 1. This is equal to little of n to the 1 plus 1 over k. For any k greater than 1. So as long as k is at least 2, n to the 1 plus 1 over 2k minus 1 is going to be little o of n to the 1 plus 1 over k. So this general lower bound is far off from the upper bound from the Bondi-Seminovic theorem when k is greater than 1. But it does have some dependence on k. So it's a non-trivial lower bound. And we're going to prove this just using some techniques that we've already seen in the class. So we're going to use some probabilistic methods, and it's ones that we've used before. So we're going to use alternations, and we're going to use that with expectations. So here's what we're going to try to prove. This lower bound that the Turan number of C of 2k is big omega of n to the 1 plus 1 over 2k minus 1. In order to prove this, like I said, we're going to use probabilistic methods. We're going to use expectations and alterations, and we're going to run an experiment to build a graph. So we'll start with an empty graph of order n. So it has n vertices, it doesn't have any edges yet. And we're going to add edges to the graph independently, each with probability p. So we have a graph of order n, and then each possible edge will include it with probability p. And this value p, in some of the proofs that we saw earlier in the class, in earlier videos, we chose p at the beginning of the proof. For this proof, it'll make sense to choose p at the end. So we'll just choose a p-value that works for us to give the bound that we want. So we're going to define some random variables, as we usually do when we're applying these probabilistic methods. So first random variable will be x. X is this random variable that is the number of edges in G. Why is it a random variable? Well, G is a random graph. So G is the result of this random experiment. And so the number of edges in G can vary based on the results of that experiment. So X is a random variable, the number of edges. And we'll define another random variable. Y is our second random variable. It'll be the number of copies of C of 2k in G. And as we usually do with the alterations, we're going to try to get rid of the copies of the bad subgraphs that we're trying to avoid. So in order to do that, we want to see what's the expectation of x and what's the expectation of y. So here's where we're going to try to use the expectation. And then once we have those expectations, we can do our alteration. So first, expectation of x. Let's see why this is n choose 2 times p. So in order to get expectation of x, we're going to define some indicator random variables. So we'll say let xe equal 1 if e is in G and 0 otherwise. And this is for any e that is a subset of V of size 2. And we'll be saying our graph G equals VE as usual. So for each E that's a subset of V of size 2, we'll say the indicator random variable XE equals 1 if E is an edge of G and 0 otherwise. And I claim then that the expectation of X that we're trying to calculate here, expectation of X, this is equal to the expectation just of the sum over these E's of XE. So the number of edges in our graph is just going to be the sum of the XE's, because each XE is going to be 1 if E is an edge and 0 otherwise. So it's just adding them up gives us a count of the edges. We can use linearity of expectation here to write this as the sum over E of the expectations of the XE's. And then we can calculate the expectation of the XE's. So expectation of XE, we can write that as 1 times probability XE equals 1 plus 0 times probability XE equals 0. And this one just becomes 0 because it's 0 times something. So we get probability XE equals 1. And probability XE equals 1, that's the probability that E is an edge in G. So the probability that E is an edge in G, each edge got included with probability P. So this probability is just P. So the expectation of XE is P. And that means we have the sum over these E of P. And the total number of E is just the total number of subsets of V of size 2. V has size n, so we get n choose 2 times P. So that's how we got this expectation. Now, we can also get expectation of Y similarly, but we'll just get an upper bound on it because that's all we need. So expectation of Y, to calculate this one, we will define some other indicator random variables. So for each sequence S of 2k distinct variables, sorry, if I said variables, I mean vertices, distinct vertices of G. So like S equals V1 up to V of, let's say V of I1 up to V of I of 2k. So just some vertices of G. And we'll say the vertices of G, like V, this set will be V1 up to Vn. Okay. So S is just some sequence of 2k distinct vertices. Sequence means the order matters in S. And we'll define this indicator random variable, Y sub S. We'll define it to be 1 if there's a copy of C2k on S. And 0 otherwise. And we're talking a copy of C2k on S. I just want to clarify what I mean for this. So a copy of C2k on S. I'm talking about a C2k where we have the edges VI1, VI2. So here's our vertices. And then the last one is VI2k right here. VI2k minus 1. These are all distinct vertices. And so we let Y sub S equals 1 if we have this subgraph on these vertices. So if we take our vertices in order, VI1, VI2, VI3, all the way up to VI2k, we must have an edge VI1 to VI2, an edge VI2 to VI3. This should be VI3 right here, sorry, and that should be VI4. So we want to edge from Vij to Vij plus 1. So we need an edge Vij, Vij plus 1, and this is for each j equal 1 up to 2k minus 1. And we also have the edge vi 2k comma vi 1. So we have a total of 2k edges, and we could also have extra edges. The only edges we must have are these 2k edges, and we're allowed to have any number of extra ones. So that's the definition of our indicator random variable ys. And y, right here, y is the number of copies of C2k in G. So I claim that y is going to be less than or equal to the sum over these sequences S. So sequences, I just want to emphasize they're sequences, not subsets, and they're linked to K of the ys. So every possible copy of C2k in G is going to be counted by one of these ys's. So the copy will contribute 1 to one of the ys's. So the sum of the ys's is going to be at least the number of copies. It's possible that the same copy could contribute to multiple ys's. So the sum of the ys's might overcount the number of copies. It's fine to overcount it because all we're claiming here is that y is less than or equal to the sum of the ys's. So if we want expectation of y, we can write this as less than or equal to expectation of the sum over S of ys. And this equals the sum over S of expectation of ys. Okay, and now we want to see what's the expectation of ys. So expectation of ys. So for a fixed S, so S is some sequence of 2k distinct vertices. So fix S. So x equals vi1 up to some vi2k. All of them are distinct. And this is going to be equal to 1 times the probability that ys equals 1 plus 0 times the probability that ys equals 0. Again, this part cancels because it's just 0 times something. So we get the probability that ys equals 1. Probability ys equals 1. So that's the probability that there's a copy of C of 2k on S. And I put this in quotations because I mean this specific copy. It has to be on S in the order of the sequence on S. So in order of S, I should write. But we've already explained it with this picture, which copy we're talking about. So we want a copy where vi1 has an edge to vi2, vi2 has an edge to vi3, and so on, all the way up to vi2k minus 1 has an edge to vi2k, and then vi2k has an edge back to vi1. So we want all those edges. So the probability that we have each of those edges, those are the only edges that we care about. So all the other edges can be anything. They can be an edge or a non-edge, and that's fine. But these 2k edges all have to be edges. So in our experiment, we have to include each of those edges. All of them had to have been included. So each of them have a chance of P to be included. All of them are included independently. So the probability that they're all included is going to be P to the 2k. So we have P to the 2k right there. And now we have this sum over S of P to the 2k. And the number of sequences S of length 2k, this is going to be less than, I'll write less than or equal to. It's less than, but less than or equal to is also true. That's going to be less than n to the 2k times P to the 2k. So the number of sequences of length 2k, sequences of vertices, so these are 2k distinct vertices of G. So we get n times n minus 1 times n minus 2 all the way down to n minus 2k plus 1, which is clearly less than n to the 2k. And we're summing p to the 2k that many times. So it's n to the 2k times p to the 2k. So that's why we got this expectation for y. And now the rest of it is pretty straightforward. So if we have expectation of x, we also have expectation of y, and now we can combine them. And I just want to emphasize again, we didn't calculate the expectation of y exactly. We only got an upper bound, and upper bound is all we need here, because our next statement is that the expectation of x minus y is greater than or equal to n choose 2 times p minus n to the 2k times p to the 2k. So all we're using here is that the expectation of x equals n choose 2 times p. So that's how we got this term. And then this less than or equal to n to the 2k times p to the 2k, when we subtract the y, it becomes a greater than or equal to negative n to the 2k, p to the 2k. So that's how we got that. So that bullet is immediate from the last two bullets. Now, if we know that the expectation of x minus y is at least this quantity, n choose 2 times p minus n to the 2k times p to the 2k, that means that when we run our experiment, the average of this quantity, x minus y, is at least n choose 2 times p minus n to the 2k times p to the 2k. If we know that the average is at least this quantity, that means that there must be some element in our set that we're averaging over, which is greater than or equal to this quantity. Specifically, there must be some graph, there must be some way we can run our experiment for which we obtain this graph G of order n, where if we look at the difference between the number of edges, so number of edges is cardinality of E, that's our x, the number of edges, and we look at the difference between the cardinality of E and the number of copies of C of 2k and G, and that's our y. So we're looking at the difference x minus y for this specific graph G. And the claim is that the difference is at least n choose 2 times p minus n to the 2k times p to the 2k. We're just using the expectation of that difference being at least that, and that means that there has to be some graph that has that difference at least that. So it's the same trick we always use when we're doing expectation for probabilistic methods. Now, what this means is that we can take this graph G and we can do an alteration on it. So we take the graph G, we look at any copy of C2k and G, and we just remove an edge from the copy. And if we remove one edge from each copy of C2k, the resulting graph won't have any copy of C2k. So it'll be a C2k free graph, and we'll call the resulting graph G prime. And that resulting graph, since we only removed at most one edge for each copy, and since the number of edges minus the number of copies is at least this number right here, that means then that if we take G and we remove one edge from each copy, we'll end up with the number of edges in the remaining graph at least this quantity. Because G, the number of edges in G minus the number of copies of C2k originally was greater than or equal to this quantity. So for G, the difference is greater than or equal to that. And this difference right here, I just want to note, which difference am I referring to? It's this difference right here, the x minus the y. So that difference is going to be at least n choose 2 times p minus n to the 2k times p to the 2k for this G. So this G has to exist because the expectation is at least that quantity. And so we obtain G prime by just removing one edge from each copy of C2k and G. And that means that G prime, like I said, is going to be C2k free. So it won't have any copy of C2k because we removed an edge from each copy. And the number of edges in G prime is going to be at least this right here. So we started with this many edges, and then we removed one edge for each of these possible copies. And we know the number of copies is at most this thing that I circled on the right. And so we find that G prime has this many edges at least, n choose 2 times p minus n to the 2k times p to the 2k. And we also know G prime is C of 2k free. So if we could just show that this quantity right here is at least the quantity at the top, then we would have the lower bound that we're trying to get. So if you could just pick P to make this quantity at least, so for what P is it omega of n to the 1 plus 1 over 2k minus 1. So can we find a p to make this quantity omega of n to the 1 plus 1 over 2k minus 1? I claim we can, and that's a problem I'll leave to you. So problem, find some value of p in 0, 1, and p can depend on n, so that's fine. It's definitely fine for it to depend on n. It may depend on n for sure. So find some p-value in 0, 1, such that this quantity right here, n choose 2 times p minus n to the 2k times p to the 2k, same thing I wrote right here, is equal to omega of n to the 1 plus 1 over 2k minus 1. And that gives us the lower bound we're trying to prove, as long as you can find that p-value. So that brings us to the end of this video. Thanks for watching.